So today we would be discussing about thermal analysis of clay pot. So in the following presentation we would be discussing some applications of evaporative cooling. We would be discussing the design of the clay pot, the principle behind the heat transfer involved, and conclusions that we can draw from this presentation. Cooling through evaporation is an ancient and effective method of lowering temperature. Both plants and animals use this method to lower their temperature. Trees, through the method of evapotranspiration, also one of the kind of evaporation, remain cooler than their environment. This is how a normal clay pot would look like. These are some properties of clay. Clay has low conductivity of heat and it's very porous in nature. It's also cheap and easily available. Let's now discuss the design of the clay pot and the principle underlying the heat transfer involved. Normally, this is how a clay pot would look like this. And it will also be having many pores in it because of the material being porous in nature. It'll have many pores, and these pores are one of the main reasons why the temperature of the water inside this pot would remain cooler than its surrounding. And obviously, because it's a water pot, it'll also be containing water inside, like this. Some water droplets living inside these pores. Now what happens is that a dry and hot breeze would come around this pot like this from both sides, from all the sides, and it would be carrying some energy with it. So the breeze contains energy which would eventually be transferred over to these droplets, water droplets living inside these pores. Now normally what happens is that the energy content of these water droplets is lesser than the breeze, so it sucks in the energy brought in by the breeze and evaporation takes place. Evaporation would take place. Here the sensible heat was converted to latent heat, and this caused the dry bulb temperature of the air to lower down. And as the temperature of the air has now been lowered, the air surrounding the pot has become cooler, much cooler. And this cool air would also lower down the temperature of the water inside the pot. So as we saw, the principle underlying evaporative cooling is conversion of sensible heat to latent heat. The warm and dry outdoor air is forced through porous wall or wetted pads that are replenished with water from cooler's reservoir air. Due to low humidity of the incoming air, some of the water gets evaporated. Some of the sensible heat of the air is transferred to water and become latent by evaporating some of the water. The latent heat follows the water vapor and diffuses into the air. Evaporation causes a drop in the dry bulb temperature and a rise in the relative humidity of the air. Now, we have obtained some results in different situations. Let's discuss. This is a temperature versus time graph when the pot is subjected to natural convection. We can see that at both 1.5 liters and 4.5 liters, the ambient temperature remains somewhat same. And the T1, which is the water temperature, at both the volumes also remain same. This leads us to thinking that the water temperature does not depend on the load. It does not depend on the volume content of the pot. Now this is a graph when the pot was subjected to forced convection. We can see different curves at different velocities, namely 0 meters per second, 2.6 meters per second, and 4.4 meters per second. Ambient temperature has, so naturally, in forced convection, when the velocity is increased, the temperature of the air is going to decrease. But it has also been observed that the water temperature sees a decreasing trend with increasing velocity of the air. The water temperature cools down much faster and cools down to a much lower temperature. The conclusions are: water in the clay pot can be cooled to the same temperature irrespective of its load, and water temperature is lower when it is subjected to forced convection compared to natural convection. Thank you.